Hi, my name is Linnea.
I'm Bezia.
And I'm Linnea, and this is episode number 6 of the Lemma Journal Club.
What is the Lemma Journal Club?
The Lemma Journal Club is a show where we read every paper to tell you if you need to read it. You probably do.
We have a terrific paper for you today. We're talking about mechanisms of skin vascular maturation and maintenance captured by longitudinal imaging of live mice. This paper is by Chenwan Kam, Ashani Singh, David Gonzalez, ... and the ... is in the official publication of the paper. And then the last authors, Edward Marsh, Karen Hershke, and Valentina Greco. This paper is in Cell, which, boy, did I not realize it was in Cell before we picked it. Cell has really long papers, and I shouldn't have done that. Published 2023. Yeah. And Lenny, do you have a question for me?
Yeah, Bezia, why did you pick this paper?
Okay, so I picked this paper because, I guess something absurd happened for episode 5. I forgot that it was a PNAS paper, and I was looking at the PDF and couldn't figure out where the videos were for episode 5. And so I contacted the lead author of episode 5 for this poll sheet paper, who, like an absolute maniac, has placed their phone number like front and center in their personal contact I am a scientist website. I should have called the person because that would have made a much better story. Instead, I just texted them and sorry, I'm getting to why I picked this paper. This is related. I texted them and said, do you have videos for this paper that I could use for the YouTube upload or for the Patreon upload? And they texted back, which is, again, lunatic. Very nice. What I heard is, you idiot, this is a PNAS paper. The videos are inline. Just download them like a normal person. They didn't say any of that. They were just like, oh, I think the videos are on the publication. They were very nice about it. They were a very nice person. But the next thing that they said is, oh, I know you. 2 weeks ago, you covered Gabriel's paper, and he sits right next to me at this desk at this job that I have. And it made me realize that unintentionally, we have covered a very, very narrow world of science and imaging, and I wanted to break away from that world. And so I wanted to break. So this is why I picked the paper. I wanted to break out towards tissue level imaging, not of cleared organisms, but of real, heavy duty. You can't get single cell resolution, not really, because you have to go through real skin and stuff. And so it seemed like a good target. Megan says that Kai came out of this lab, which makes a lot of sense.
Okay.
Yeah. And there are many things that are harder than vasculature in mice, but I think vasculature in mouse skin is about as hard as you can get and still get an image using a microscope, right? So this is kind of towards the edge of what's possible. That's why I picked the paper. I'm used to us doing journal club with a bunch of people, like 6 or 7 people, such that the rotation is that I get to pick a paper once every 2 or 3 months. And so I put a tremendous amount of stress into what paper I'm going to pick. I assembled 5 or 6 papers that I wanted to do for journal club. I sent some of them to you. I kept going, no, actually, we're going to do this paper. No, actually, we're going to do this paper. I did to you over and over again. I've done it to you last week. I backed out of my pick at the last second because I got too nervous about it. I've got to get more comfortable with I get every other pick. We'll go through all the papers I want to read. And so this was a good pick. Yeah.
Yeah. Are you feeling pick regret off of this
I'm
paper?
not feeling pick regret. But in the first 2 paragraphs, it's quite heavy on nomenclature that I'm not familiar with, that I know that you're not familiar with. It's very clear that it's a paper outside of our fields. And I was worried that it was going to be too far out of our fields to have a meaningful conversation about. I don't think that's true. I imagine that you just have a giant, you've just highlighted the entire paper in red.
Just the first page. Are we skipping the speed read?
We're skipping the speed read. We're not doing that anymore. We got a lot of feedback, all of it given in a place of love. We're incredibly grateful for the feedback. Yeah, I should have said it at the very beginning. I was like, the first thing I'm going to say, this is the best part of my week, this journal club.
Oh, yeah.
I spent the whole week looking forward to doing this with you. So I'm pretty excited, even though it's covered in red.
Okay.
Because we're not doing a speed read, just super briefly, if you haven't looked at it before, you could go look at this paper, read the paper, and then participate in this journal club and yell at us on your computer for getting things wrong. This paper, they're using some very fancy microscopy techniques to look at neonatal endothelial cells, so endothelial cells in this case, make this capillary vascular network. They call it the capillary plexus. I don't love the word plexus, but whatever. And they're basically looking at how does the capillary vasculature system of these endothelial cells change from 5 days after a mouse is born to 35 days after a mouse is born. That's the basis of the paper. And in order to do that, the reason why I picked the paper, you have to use a microscope to image through a mouse, right? You have to go through the mouse skin to the vasculature, which is real difficult. You don't get to see beautiful, incredible single cell resolution in an image every 5 seconds and do light sheet and stuff like that. It's not on the table. You have to go with very different techniques.
But their images, they have made beautiful.
Yeah.
Like their supplementary figure 1, which I was shocked had to be a supplementary figure, but
especially for Cell. Is there a page limit for Cell, or are they just like it's not allowed to be a book? It's the only rule for Cell.
There is a figure limit.
There's a figure limit.
Yeah.
Okay.
So they hit the figure limit, and that's why so many like beautiful and important results were pushed to the supplement, I think.
Oh wow. I didn't see half of this. Oh my God. Yeah.
But if you read the paper on the website, which I never do, I always download the PDF. But if you read the paper on the website, the supplemental figures are in line.
Yeah.
Yeah. And the supplemental movies.
Yeah. I always download the PDF because I annotate the PDF with this readcube.com. Do you annotate it with something?
I just am reading it in the Mac and I annotated that.
Yeah.
That way.
I do the ReadCube so that it syncs between different computers.
That would be nice. I should do that. I just ReadCube always pops a lot.
This is why I missed the videos in the previous paper, is because the inline videos aren't there on these PDFs.
Well, so in the summary, I highlighted 3 things.
Okay.
Capillary plexus expansion, which I think, having read the paper now, is the growth of this network right next to the skin, of blood vessels right next to the skin. And that this network is for some reason called a plexus.
Yeah. So there's, and they have this, you were talking about the supplementary figures. They have supplementary figure 1C. It's the superficial plexus on the top of the skin, the intermediate plexus further down, and the deep plexus where you're getting far enough down in the skin that you're starting to get arteries and veins. They call it a plexus. I don't love that word, but whatever. It's a word. And the expansion of the plexus is that when you're a little tiny baby mouse, you have this very dense plexus, and that over time, this plexus becomes sparser. It kind of looks like
also physically larger.
Well, I mean, the mouse is becoming physically larger.
But anyways.
But I don't see that the individual capillaries, like the bubble size. I think of this as a foam, right?
The bubble size is getting larger.
The bubble size of the foam is getting larger.
The individual capillaries are not?
I don't see it in the images. I mean, maybe it's like slightly true, but it doesn't look obvious to me.
Okay.
What else did you highlight in red in your first paragraph, in the summary paragraph?
What else did I highlight in red? Vessel regression, which again, they explained in the paper.
Yeah.
And then...
Do you want to explain vessel regression for our listeners?
Vessel regression is where you get rid of a branch, essentially, of your blood vessels.
Yeah, but Keeley, like they show not by apoptosis.
Yeah.
The branch like sucks itself back in and it helps expand the other parts of the foam.
But I think that you would call it vessel regression even if it was apoptosis.
Yeah. But they just show that.
They show that in the paper.
And I was shocked throughout the paper. They keep saying essentially over and over again, there's very little apoptosis in this system and there's very little proliferation in this system. And this is just a rearranging system.
Yeah.
And I say that all the time about my system. And so like 2 possibilities. 1, there's just like much less proliferation and apoptosis in developmental biology than I thought there was going to be. Or 2, we're much worse at spotting apoptosis and proliferation than I thought we were. Because I seem to be very good at spotting it when I started out. But if it's not, I'm like shocked that it's not in the system. But I think a lot of people are shocked that it's not in my system. So
Yeah. Maybe it's just not as prevalent.
Yeah.
I mean, they did like fairly convincing experiments.
Sure.
For that.
But they do the same experiments that I do.
Yeah.
And so now
maybe they're just not good markers for this.
Yeah. I think a lot of people are like screaming at us over the internet. Of course they're good markers. But look, it's weird. It's weird. It's weird that it's really weird to me that there's no proliferation in the system. Well, what's the third thing that you've gotten read on your summary?
The third thing is my favorite, is plasmalemmal.
I've also gotten read plasmalemmal self-repair response. I'm assuming you looked it up.
I didn't look it up.
Oh, you didn't look it up?
I didn't have time.
No.
But I liked that it was lemma.
If you same reaction. If you had to guess what plasmalemmal meant, right? If you just had to guess what a plasmalemmal was.
I think it's something to do with the membrane.
Oh, yeah, pretty good. I think, as far as I can tell from actually looking it up, it is synonymous with cell membrane.
Okay.
So it could just say through a cell membrane self-repair response.
Okay.
And it's like, murine versus mouse. It's plasmalemmal. So we could like start talking about that. We study, the plasma. Anyways, it's a ludicrous word, but I kind of like it because it kind of has our name in it.
Yep.
Should it be the Lemmel Journal Club?
For the title of the...
for the title of the whole episode, the Lemmel Journal Club. That's pretty good.
Plasmalemmal.
Yeah. I essentially had the exact same things highlighted in red.
Yeah. And they took a while to define them, but now that I've made it through the paper...
I just Googled them.
Immediately. I just feel Google is broken and I'm on a AI boycott, so...
Yeah. This is... Celeste does -no AI or something like this, or maybe -AI or something, automatically like strips the Google search of all AI. I don't do this, but it is what one should do if you want to get the vestiges of what remains on the internet, which is nothing. Okay. So for going back to the no proliferation, only rearrangement. So like, I was confused. Is this a hard and fast rule for adult vessels? Like, no, I'm shocked by this.
You can proliferate if you if you get a burn and you get rid of a ton of your capillaries.
Yeah, I was thinking, I don't know what the answer is, because I was thinking they do this towards the end of the paper, they do a chemical ablation where they just screw up a bunch of endothelial cells. I think it's like 30% of endothelial cells all at once with this tamoxifen-induced chemical ablation. And I was like, what is that? In what situation biologically does something like that happen, where you just lose 30% of your endothelial cells at random? And I was thinking, maybe this could be like some offshoot of like a second or third degree burn, right? That like deep tissue blood vessels are just randomly getting killed because of heat shock.
Or a chemical burn where you get bleach or something on your skin.
So you could kind of imagine that something like that could happen. And these results would show, no, you don't. At least on the timescales that they study, which is like a month.
Yeah.
On the timescales of a month, it's not getting healed via cellular proliferation. It's getting, healed. The foam is getting recreated by endothelial cells spreading out and rearranging and doing their best.
I found that wild. And the other question that I had is I'm a runner and there are all of these studies about for humans, if you run a lot, you're supposed to increase your capillary. And so are you not increasing the number of these epithelial cells? So you're just increasing their length and connectedness?
One thing that is not here so much, I know that I'm just going to Command F for it real quickly, is there's not so much angiogenesis here.
They do a little bit of angiogenesis, but I think they say that they were surprised that a lot of the rearrangements were due to vessel regression rather than angiogenesis.
Yeah. And then, they say this very confusing statement. They say, in accordance with previous studies, vesicles undergoing regression were indistinguishable from those undergoing angiogenesis, as 70% of vessel sprouts tracked from P5 to P9 resulted in regression. So, they have difficulty telling the difference between regression and angiogenesis, which I found super confusing.
Well, I think it's you can't, from a still frame, you can't tell whether this is a waxing or waning moon, right?
But literally 3 sentences before that, they say, during P5 to P15, so day 5 to day 15 after they're born, show that vessel regression significantly outpaced angiogenesis at both the P5 to P9.
Right. So they have time resolution. So they're able to eventually track that it grows or it shrinks. But if you're just to take a snap where it's either growing or shrinking, you can't tell from that snap.
So the sentence is vessels undergoing regression were indistinguishable. I see. In a single time frame, the vessels undergoing regression are indistinguishable from those undergoing angiogenesis. And they know that because they don't just have a single time frame, they have multiple time frames.
Yeah.
I see. Okay. While we're looking at these two paragraphs, they say that they report some area in 300,000 microns squared. And I remember writing my foam paper and having a similar number, which was like 100,000 microns squared or something. And one of the reviewers was like, do you mean to say 0.5 millimeters by 0.5 millimeters? Please use units that someone could understand. I thought that was a pretty good reviewer comment, which they didn't have this reviewer, so they didn't get that. But yeah. So it is interesting that as soon as we go to these like tissue level experiments, especially for vasculature, for cardiovascular stuff, your mind immediately starts to leave like, oh, what can I measure in science? What is the biophysics of these foam-like vasculatures? And immediately starts to go like, when I work out, it's so quick to like make the jump to medical. Yeah, it's very dangerous.
Yeah, relation to our own.
Yeah.
Yeah.
They do. I mean, maybe this is not the right time to go to it. Maybe we'll talk about the mechanism stuff at the end. They do start with supplementary figures, which I feel happens a lot. And I always feel like something has gone off the rails in the revision, like reviewer response thing, when you start your story with supplementary figures. But you're saying supplementary figures are in line in the online
version. Yeah. I have it up here because it's really very pleasant and was the only way that I was able to engage with the figures, because cell papers are so huge. How do you flip between the figures and the main text in a normal PDF? But yeah, they have the supplemental figures in line. And I think this is a quirk it's because Cell allows you to publish really long papers, but they do have a figure limit.
Yeah, I feel like you never wrote a paper with the intention of the very first thing you said going into the supplement, and that this is just like something has happened during massaging and now it's done. It's whatever.
It's done, yeah.
They say they conducted their studies in palmoplantar skin. Do you know what palmoplantar skin is?
I didn't even catch.
And they said
it's the mouse palm.
I have no idea. Good.
They have the nice
palmoplantar. That sounds
and plantar fasciitis is some sort of foot.
Yeah. And then they say, as this anatomical region offers a simplified model devoid of cycling appendages.
Yeah, that I highlighted cycling appendages.
This is the sentence where I was like, I'm not going to look those words up, and I might be in too deep. Okay. So then. One of the tricks.
But should we admire the experimental, work that had to be done here, where you're taking a mouse paw and you're putting it under the microscope and you're somehow imaging the same region of blood vessels every time?
I literally started groaning towards the end of the paper, where they would be like, and then a month later we found the same exact spot. I took another image. I'm like, what the? Because okay, sure. They probably circle on permanent marker the little bit of the mouse, and they make sure the mouse is in the exact. It's just if I did this on a sample where the sample was embedded in glass and it's not moving and everything was perfect and it's a super easy sample, this would be such a painful experiment. And then you're doing it on an alive animal.
I assume sedated, right?
Some author, it's not necessarily the first author, although I would guess it's the first author. Some author here has unbelievably good hands when it comes to experiments. To be able to find the exact same pattern of vascular system so that you can say, hey, this is the same thing that I imaged 20 days ago. And now I see that it's changed just a little bit, and I'm going to make a time lapse that way is, if I didn't literally see the images, I would be like, I don't believe it. I don't believe that someone can do that. Right. Because it's just so massively painful. Yeah. Are you not going to ask about their year one little yellow and gray things that they drew about the places where there is blood flow and the places where there's not blood flow.
Yellow and gray things, figure 1.
So figure 1E has like these orange bits of vascular.
Oh, I'm looking at figure 2. That's fine.
And these blue bits of vascular, right? And they call these perfused, which means that blood cells are moving through it.
Yeah.
And non-perfused, which means that blood cells
aren't. Did you look at these beautiful movies?
Yeah, that's why I picked the paper. It's the beautiful movies. Just I scrolled through this paper, saw the beautiful movies, was like, well, I don't know any of the authors on this, so I think I can use it because, I felt that we couldn't use other papers, and that's why I picked it.
So why are red blood cells? So I guess the first question I have is, do you know, I'm sure it's in the caption, I'm sorry, if E was generated by this red blood cell free harmonic generation tracking?
Yeah, so that's exactly, they've done a video of it to figure out where the perfused cells are, to figure out where the red blood cells are actually going through.
Yeah.
And then they're like, look, this part of the vasculature is useless. There's no red blood cells moving through it. This part of the vasculature is not useless.
Yeah.
And then they kind of show over time, the vasculature becomes like the bubbles in the foam are getting bigger. The gaps between vasculature are getting bigger. The length scales are getting bigger.
And perfusion is better.
And the perfusion is better. It's optimizing the network.
Yeah.
I think, again, like clearly foam is not the right way. Like it's in 2 dimensions, this looks like a foam.
Yeah.
But this is a bunch of tubes in 3 dimensions. And they make a very weird claim about the 3rd dimensionality of this system that I don't love. But these are not sheets. So this is not a foam. How would you describe this like lattice of tubes?
Yeah.
It's like a hollow foam or a non-sheeted foam or something.
I mean, vasculature.
Vasculature, sure. Just describe it with itself, yeah. Okay, so I looked up how 3rd harmonic generation works for the first time in my life.
Well, I wanted to know why it works on red blood cells, so maybe you'll get there.
So the basic principle of the 3rd harmonic generation, right, is so 3rd harmonic generation does not pick up on the like entropy of molecules. So only the even number harmonic generations, mostly 2nd harmonic generation, but also 4th harmonic generation, pick up on the anisotropy of molecules and can tell you, all these molecules aligned or anti-aligned. That's what we're familiar with. We've done a lot of SHG work for people who are 2nd harmonic generation work for people who are not. I don't think we've ever published any of our 2nd harmonic generation work, but we got to learn a lot of things that we never shared with the world. I think that's how we started dating, was our 2nd harmonic generation work, more or less. Yeah.
I think that's true. Yeah.
That's the first picture I have of you
time together.
was you coming back from a Frisbee match, just covered in mud in the lab, trying to put together this sample at like 10 p.m. for us to try to take a 2nd harmonic generation. And I thought it was a pretty funny image. Okay, so 3rd harmonic generation doesn't go like that. What 3rd harmonic generation does is it should cancel out everywhere and you should get nothing back. But it has a funky lobe to it for its excitation. And so wherever you're pointing, it tends to sample a little bit above where you're pointing the confocal microscope and a little bit below wherever you're pointing the confocal microscope. And if the place above and the place below have different refractive indexes, have different n, then there's no longer a destructive interference between the 3rd harmonic generation and you get a signal. And so what it does is it really highlights changes in refractive index, specifically in 3 dimensions, right? So that's pretty cool already. So this thing picks up on changes of n, of refractive index, that occur. And there's a few other things that can kind of pick up, similar to SHG. There's some blurring of the lines here and stuff like this. But more or less what you should think of it is picking up changes in refractive index. And specifically what we're seeing with red blood cells is the change of refractive index of something that's dense in hemoglobin. So that's why it's picking up the red blood cells. And so this is with a 2-photon laser? That I do not know. Okay. I thought, looking up how 3rd harmonic generation works, is like, I know with a 2-photon laser, you can get accidentally 3-photon excitation and emission, and that's kind of a thing that blurs your 2-photon imaging a little bit. I do not know if with a 2-photon laser, you're going to always get these higher harmonics, but do you get them enough? I don't know. Okay. What I do know about 3rd harmonic generation is the 2nd harmonic generation has this pretty tight you take the wavelength that you're imaging at, you divide by 2. That should be where your second harmonic generation is coming back, because it shouldn't have anything to do with the fluorophores or the autofluorescence. And so you really should be able to do a quite tight filter on second harmonic generation. In the same way, you should be able to do a very tight filter around third harmonic generation. There is some blurring again because there's like vibrational modes and a bunch of stuff, but I got into like the weeds of these articles of like, here at this interface, you get a shift that moves it like towards the more red because of this thing and that thing. But you should be able to put in a pretty tight bandpass filter and just collect the third harmonic generation. Okay. So I would guess that you can do this with a 2-photon. The question is...
scroll down to the methods and they say for imaging of blood flow via third harmonic generation, they used a coherent 2-photon laser, which was tuned to 1275, allowing for label-free detection of red blood cells.
Yeah, so that's pretty cool. I did read it being like, ooh, is this 3-photon? But I guess it's not. But that's kind of cooler.
Yeah, it's very cool.
Because this is a thing we could use.
Yeah, and it's a thing that... Yeah, we've done second harmonic, and to think about what the third is giving you is pretty.
So my understanding is that it's far easier to do third harmonic generation than second harmonic generation, because you don't have to do this pretty complicated filter setup. And in second harmonic generation, because you can, there's a large onus to like normalize by density correctly. In third harmonic generation, I was looking it up, and it's, you can normalize for depth via fluorophore, but you can't quite normalize for density because you can't quite get the index of refraction separated purely from like, is there more hemoglobin or is, you can't quite do that.
I see. But they're just looking at movement here.
Yeah, they're just looking at movement.
I don't know, maybe they did PIV or something to see whether the thing is moving.
Oh, I think they just by eye because they just drew in those things on E, right? So I don't think there's anything as fancy as PIV here. It is cool, right? It's a pretty cool thing. We could go after changes of index refraction using this system.
Yeah, it's very cool. And then I thought that this was a super important result in the paper. Like they put it up front, that this is really like this rearrangement is improving the function of the network. It was not immediately obvious to me looking at the networks, because I would have thought that, for capillaries, you want a lot of connectivity so that you get blood everywhere, but that's not quite what they're optimizing for.
Yeah. And so what they say is, as we track these vessels, we found that the percentage of non-perfused means there's not red blood cells moving through it. The percentage of non-perfused vessels was reduced over neonatal development. Furthermore, the majority of vessels fated for regression were non-perfused. 90% of vessels fated for regression were non-perfused. I guess that's not the entire paper, but...
That was my favorite result.
That's the reason why we're reading the paper. That's why we covered this with those videos that eventually led to those results. So then we get to the really, really weird results. I don't say weird as in skeptical. I just, wouldn't have guessed this, which are these, the rearrangement, the regression and everything, the rearrangement of these vessel systems is due to cells migrating, due to cells extending, but not due to division in cells or apoptosis of cells.
Yeah. Yeah. And I was a little confused during the growth phase, going from neonatal to juvenile to adult. They were saying that the rearrangement of cells was impacting cell density in some way, but I couldn't quite follow what they were. Did you follow this, or was this important? Like, is cell density changing over time? I think they were saying that the cells grow.
I got the impression that this was like a little bit of like how you define density.
Okay.
And they, analyze things a lot of different ways. In some ways that they analyze things are not significant. In other ways they analyze them, they are significant.
Also, this wild A prime, B prime.
Is that normal in cells?
No, I've never seen. Well, I don't know. I haven't read that many cell papers.
That's what I do. I do the A prime, A double prime when I'm prototyping figures, and I'm writing things kind of sloppy, and I don't want to have to go through and change every single thing if I'm writing like Microsoft Word or something. To see it in the final, it's fine. It's fine.
It's interesting, because it tells you which plots go to which images is the nice part.
But my overall impression with it, the cells are getting longer and the spacing between the plexus or the plexus length scale is getting larger.
Yeah.
And how you want to talk about that for density kind of depends what length scale you're looking at. I didn't think that there was anything super profound about this, other than that they are rearranging and they're going via migration, and they're just quantifying that a bit to say, look, hey, this is not via cell proliferation. We're not just getting more cells everywhere or something like this,
Yeah. The other thing I found interesting in this migration section was the videos or the images of the cells moving upstream.
Yeah, they move against the blood flow.
Yeah, which, is it obvious why that would happen?
Or what the mechanism for movement is in general? I mean, I think the why it would happen is they have to be able to sense the blood flow somehow. If the blood flow is going to be what helps you have information for how you want to rearrange your network. Mm. And so you could imagine that migrating up the blood flow helps make that automatically happen. This is not a physics paper. I don't think it was intended to be a physics paper. This is not entirely true, but I think in general, if you're in cell, you're pretty far away from physics. But this system is incredibly rich
for biophysics.
So
this reminded me very strongly of some of Arnold Matheson's work at UPenn. He does bacteria swimming upstream, and this is like a known thing that's been rheotaxis that's been studied for a long time of how they get. Yeah, it's obviously beneficial for bacteria to be able to get into liquid hosts, I think, by swimming upstream.
A reason why I got so interested in this from a biophysics perspective is, to me, this is not familiar of any biophysics system that I am seeing people studying. That it's not a foam, it's a vasculature, as we said. The rules are super simple, but different rules. It's like a little bit different from every system that I've been thinking about.
I want to think a little bit more about this vasculature thing, because you say it's not a foam so strongly, but there is stuff in between. It's not like there is, if you think about a leaf.
There's no surface tension here.
There's no surface tension? I know
there's no analog to surface tension. At very best, there might be line tension here, but there's no surface tension here. It's got essentially it's embedded in 3 dimensions, just like a foam, but it has a fundamentally different dimensionality in my mind. There's no sheets. It's just lines. I mean, it's tubes, but
It's tubes. It's a 2-dimensional foam.
It's a 1-dimensional foam?
It's a 1-dimensional foam.
I mean, foam is a 2-dimensional foam in my mind. Like, it's a 2D structure embedded in 3D.
Yeah.
Right? Here, to me, this is like a 1D structure embedded in 3D. It's a bunch of sticks making a network in 3D.
Okay. But there is line tension, right? Well, I mean, maybe not. Maybe that's not an important quantity here, but
with a foam, right, you can do measurements on the foam to get, for instance, an elasticity of the foam, right? It's a weird measurement to do, but it's a common measurement to do,
sure.
Right?
Don't you think you could take a slice of this thing and do...
I don't know.
Or if you let's say you were able to grow the vasculature in agarose or something. You don't think that would change the properties of that?
I'm sure that somebody has done that, and I'm sure that it does change the properties of it, and that's an interesting thing to think about. But one thing that I think is worth noting here is they have this paragraph in the paper. Given that our analysis of plexus expansion was performed within the XY plane, they're just showing XY slices, we sought to determine if similar principles of network expansion applied to the XZ axis.
Yes, supplementary figure 5.
To our surprise, we did not detect appreciable expansion of this network in the XZ plane. And instead, the same vessel structures were found at corresponding depths across revisits. To me, this implies that there is, the XY plane and then something else going on in the Z plane, and that should change how I'm viewing this structure in 3 dimensions. That it is not a genuinely 3-dimensional structure somehow.
I think that's correct. It must somehow be linked up to the other vasculature networks. Okay. First, we'll go back to figure S1, right, where they have these superficial plexus, which is, I think, what we're looking at throughout the whole paper. And then this intermediate plexus and this deep plexus. And so the superficial plexus is what they're saying isn't changing depth.
Yeah.
It's somehow linked in 3 dimensions to these other plexi.
Yeah. I mean, The whole thing is it's a super rich system.
Yeah, it's a super rich system. I'm going to make I don't know.
They don't have like a 3-dimensional reconstruction of it anywhere.
Yeah, which is, they probably
I don't know.
Could.
I don't know if that's true, right? Like, again, this paper was picked because this is a good example of doing the best imaging that you can in a system that is incredibly hard to image.
They do say, like here in figure S5, 0, 20, 40, 60. So maybe they're just not able to like reasonably connect them.
Yeah, right. Like in 2 photon at 1,200 nanometers, right? Like your Z resolution, I don't know what objective they're going in with, but at very best, your Z resolution is realistically like a micron. More likely the Z resolution is like 5 microns. So it can be tricky. It can always be tricky to do things like this. And that's why we picked the paper, is because you don't get unbelievably beautiful images when you do something like this.
Yeah, but the expansion of the network is incredible, and the fact that this is a month different. The time scales are. This is hard. This is like genuinely. It seems hard to me. Like maybe this student.
I'm very happy with what I learned how to do in my postdoc. I saw images of people who had been in my lab previously, and I was like, "Holy shit, that's the scale that I want to be able to take images at." And I'm happy that I learned that. I wish I knew how to do this. This is the next step to me. Is like, let's go up in scale. One more step so I can do everything from microtubules to like somebody's arm, right? Like,
if you get this, you can go spend a few months with Kai.
Yeah. So let's see. They do this labeling using MTMG they put in essentially a couple green cells by dosing just a little bit of tamoxifen into the mouse's water or something. And then they do laser ablation. They mess with the cells. And they find this pretty interesting thing that in an adult cell, right, this is the plasmalemmal, in the adult cell, the cell is like, I'm not going to die. I'm just going to repair myself. But in the neonatal cell, the cell just kills itself. And this makes a lot of sense to me that like if you're trying to rearrange your network and everything already, and you're going to get sparser, you're totally fine to have cells die if something goes weird. But once you're really not rearranging it all, because they really show that as you become more adult, these networks don't rearrange very easily. There's like a big incentive to do not let a cell die. Keep going with what you've got.
Yeah. And I mean, I guess the question that I had coming out of these results was like, can a cell divide here? Do they ever see cell proliferation, or is it not possible,
must be possible
in an adult system? It must be possible, you think?
Yeah, I think it's just a rare event, but it would blow my mind if it's not possible. And I thought it was interesting that like I normally think of like the younger system as the system that's more able to deal with damage. But because of the way that this is developing, there's kind of like an argument that it goes backwards here. One thing that blew my mind towards the end of the paper is when they do the chemical ablation. They ablate 25% of adult endothelial cells, and the animal survives. It's crazy to what extent this vascular system is able to fix itself up. I mean, maybe it's because it's the superficial vascular system, and you can just have really bad blood flow to your skin, and that's okay. I don't know.
This is in this network-wide ablation of adult ECs section.
Yeah. But I am shocked that you can get rid of a quarter of the cells and the network can recover from that. So we should start to wrap up because we've got to go get Asya. What do we think is intellectually beautiful about this paper?
Yeah, I mean,
I think looking at this blood flow thing is what did it for me. It's like they do this. We're skipping at it because we're kind of out of time. They do this thing where they go after this VEGFR2 signaling mechanism in the very last 3 paragraphs of the paper. If they weren't, I kind of assumed that they were forced to do that. That just like when you write a biology paper, you must give a molecular mechanism, which means you must give.
This is the last figure?
Yeah.
I was like, I really wanted figure S1 to be in the main paper. This thing to go to the supplement.
Yeah, but I think that this is the like, and we're going to talk about this on almost every single biology paper that we do. This is the dogma: is what is the mechanism?
Yeah,
it's a super
and
addictive.
it's also right. If you're in the field, I'm sure you don't care about figure S1, right? Yeah. And it's just because I'm so far afield that
But it's this super addictive, what is the mechanism framework that sounds really good, that is really helped me a lot. And I think it is more often than not just a drug, right? That the framework is a drug that you take to make your paper feel
it's
better.
Not that you use a drug to get your framework.
They do. They employ a drug, DC-101, a potent and specific inhibitor of VEGFR2, and then they show some stuff that is backwards of what I would have expected or what I think they said it showed, but I don't know because this part, screw this part. It's short. It's at the end of the paper.
Okay, but what did you find intellectually beautiful about it?
I found intellectually beautiful the first part, which is looking at the blood flow and seeing that the bits where the blood was not flowing through is the bits that got rejected from the network. Those bits regressed and the network expanded without building new cells. And the network was able to get a more efficient blood flow network by having cells migrate upstream. And you got that intellectually by looking at where does the blood flow. You did some dynamics.
Yeah, I think I found that very beautiful as well. And I would be excited to see some modeling.
Okay, so we're going to have to go get Asya soon. And so I wanted to end, one of the things that we were suggested was to synthesize some things for people who did not read the paper. And we were talking about who are we making this podcast for? And the answer mostly came down to, I'm making this podcast for you. And that always kind of turns into I'm making this podcast for Asya. So if we'll have kind of a summary for Asya at 2 levels, right, before we go pick her up. So one is broadly in the world, why did we, your parents, care about this topic? And so I think particularly your father got me. I'm your father. This is just for us now, this last little segment. We'll see how it goes. I got really obsessed with when something goes wrong in the biology of a human being or a pet or something, how do we find out what went wrong? If your dog is sick, how do you find out what went wrong? And, you go to the doctor and you get an X-ray and you get an MRI and you get images of what does the system look like. And that can maybe help you figure out what you could do to alleviate some suffering. And I looked at the tools that I had, which was mostly microscopy. And microscopy is not very good at this unless you take an explant, unless you cut out a little bit of the dog or of yourself and put that under a microscope. And so I started to look around kind of in the 2020s. What can you do with a microscope on a living organism to see what's going on and what's going wrong in that living organism? And for the most part, the only thing you can really do is multiphoton microscopy. This is not totally true. I met a person recently who's doing UV microscopy during surgery. There's all sorts of things. But the thing that I focus on is, hey, I know a decent amount of multiphoton microscopy. You can go maybe 1 millimeter, 2 millimeters deep. Can you go 3 millimeters? Can you go 4 millimeters? And if not, what can I do? That's broadly why I cared, is I wanted to be like, is there anything we can do for diagnostics here so that when my friend gets sick, I can contribute to easing their suffering a little bit with my scientific research. The second summary for Asya is specifically, scientifically, what was this paper about? So, Lenny, do you want to say specifically, scientifically, what was this paper about?
Sure. This paper was about mouse foot vasculature growth.
Okay.
And specifically that the network grows by reducing the number of branches to increase the perfusion of blood. And it does this in this really beautiful way of migrating cells rather than killing the cells. I think that's the short and sweet of it.
Yeah.
And we want to emphasize to anybody whose work we do talk about and does listen to this that we love the papers. Like, we talk about them because we find them fascinating.
Papers are emotional.
Yeah.
They're emotional to write. They're emotional to read. It's years of people's lives poured into some pretty archaic text. If you do like this, send it to other people. I think that's going to be the main way that people learn about this. And I cannot encourage you to do that enough. If you don't like this, send us some criticism. We'll cry a little bit and then we'll brush ourselves off and we'll grow from that, as every scientist does. And we're going to go pick up Asya. Asya, if you're listening.
Asya, baby.
However many years ago we came and picked you up. So we'll see you soon. Bye.
Bye.